When dealing with numericals on harmonic oscillator in the context of canonical ensemble, we need to identify whether the oscillator is a classical oscillator or quantum oscillator. So first we'll talk about classical oscillator. Now for classical oscillator, they might ask find the average energy, or they might ask find the specific heat. So for that, first you have to write a Hamiltonian. So Hamiltonian will be P squared by 2m plus V of x. Now, here we are going to calculate the average value using the continuous formulation. So instead of summation, there will be integration. So if I want to find the average energy, I have to find the average of these two terms. So the average of this kinetic energy term will be equal to integration P squared by 2m into the probability distribution. So it will be minus P square beta by 2m dp. And at the denominator, we'll have the partition function in continuous form. So e to the power minus P square beta 2m dp. So we have to calculate this integration. Similarly, for the potential energy term, we need to calculate V of x e to the power minus Vx beta divided by 2m dx divided by the partition function. So Vx beta 2m dx. Now, for such type of integration, we have some formula that will be frequently used. So I recommend you to know this formula. So integration of minus infinity to plus infinity, x to the power n e to the power minus a x squared dx. This integration is given by gamma function of n plus 1 by 2 divided by a to the power n plus 1 by 2. And sometimes they might give a nonlinear oscillator where the potential term, it might have x to the power 4. So in that situation, you can use a more general formula, minus infinity to plus infinity, x to the power n e to the power minus a x to the power b dx. This should be 0. So this is given by 1 by b a to the power minus n plus 1 by b into gamma of n plus 1 by b. So this is a more generalized formula. And sometimes they might ask find the specific heat. So for that, you first calculate the average energy, then you differentiate it with respect to temperature, then you'll get the specific heat. In the case of quantum harmonic oscillator, they might ask the partition function, but generally it's not asked, but they might ask to calculate the thermodynamic variables. And for calculating the thermodynamic variables, you need to know the partition function. So I'll just show you here how we find the partition function of a quantum harmonic oscillator. So we know the energy of quantum harmonic oscillator, n plus 1 by 2 h bar omega. So this is a 1D quantum oscillator. So if I want to write the partition function, so here it will be the discrete formulation because the energy is discrete. So minus beta En. So if I substitute this, it will be e to the power minus beta n plus 1 by 2 h bar omega. And the summation will run from n is equal to 0 to infinity. Now, here I can take out the constant term here. So it will be e to the power minus h bar omega by h bar omega t by 2. I can take this outside, and you are left with the summation e to the power minus n h bar omega beta. So now using mathematics, we can find the sum of this series term. So you can refer any standard mathematical physics book, and you can find this sum of the series. So here I'll write the final expression. It will be z is equal to e to the power minus h bar omega. So I can substitute kbt here. So it will be 2 Boltzmann constant into t. And this will be given by 1 minus e to the power h bar omega into kt. So this is the partition function. We can simplify further, and we can write this as 1 by e to the power h bar omega 2 kbt minus e to the power minus h bar omega 2 kbt, and this you can write as 1 by 2 sine hyperbolic function of h bar omega 2 kbt. So this is the part expression of the partition function of a quantum harmonic oscillator. Now sometimes in the question they can ask to find the energy. So energy, you can use the expression. You can use this expression, or you can even use this expression to find out the average energy. Then they might even ask for free energy, or they can even ask find the specific heat. So to find specific heat, we can differentiate this, that is the average free energy with respect to temperature, and you can even find the free energy, that is the Helmholtz free energy. This is a very recent question. It was asked in GATE 2023. So a simple harmonic oscillator with angular frequency omega is kept in equilibrium at temperature T. So it is a canonical ensemble, and frequency is given, and we have to choose which one is the partition function. Now we already know the formula. Z is equal to e to the power minus h bar omega by 2 kbt divided by 1 minus e to the power minus h bar omega kbt. Now if I substitute the value of omega, then I'll get h by 2 kbt into omega is 2 kbt divided by h bar. Here h bar should be there, yes. So divide now 1 minus e to the power minus h bar omega, so it will be h by kbt into 2 kbt by h bar. So here we can see that h bar cancels out with this 2 we can cancel out, 2 we can cancel, and here also we can similarly cancel, and we get the expression e to the power minus 1 by 1 minus e to the power minus 2, so which simplifies to e divided by e square minus 1. So this is the partition function at that particular frequency. So option A is the correct answer. In this question, we are given a 1D quantum oscillator, and we have to find the average energy. So first we need to write down the partition function. So here we'll use the sine hyperbolic expression of the partition function of quantum oscillators, that is 2 sine hyperbolic beta h bar omega by 2. And we can find the average energy by using this expression So you can pause the video and do this differentiation. Here log will be there 2 sine hyperbolic beta h bar omega by 2. So you can differentiate this, and I'll write the final expression here. It will be h bar omega by 2 cot hyperbolic beta h bar omega by 2. This is the answer. So we can see it matches with option A. In this question, we are given a 1D harmonic oscillator. It's a quantum oscillator, and we have to find the Helmholtz energy. That is the Helmholtz free energy. So first, let us write the partition function. So partition function is e to the power minus h bar omega beta by 2 divided by 1 minus e to the power minus h bar omega beta. So from this partition function, we can find the free energy using this formula. This is equal to minus kBt log of the partition function. So if I substitute this, see here I'm not using the sine hyperbolic form because the options are in the form of exponential. So that is why I'm using the partition function in the exponential form. So it will be minus kBt log of e to the power minus h bar omega by 2 divided by 1 minus e to the power minus h omega beta. So now I can expand this log expression. So if I expand, I'll get 1 minus kBt log of e to the power minus h bar omega beta by 2. Then here you'll get minus and minus plus. So k beta t log of 1 minus e to the power minus h bar omega beta. So if you simplify this, you'll get f is equal to, this one will be kBt h bar omega beta by 2 plus kBt ln 1 minus e to the power minus h bar omega beta. So here kBt and beta will cancel out. So the final expression is h bar omega by 2 plus, so in the option they have given, so this kBt I can write beta inverse log of 1 minus e to the power minus h bar omega beta. So this is the answer. I think it is matching with option B. So option B is the correct answer. In this question, we are told to find the value of free energy per oscillator for a 1D oscillator in the low temperature limit. Now, to identify whether this oscillator is a quantum oscillator or a classical oscillator, we can see in the options h bar is given, so they are referring to quantum oscillator. Now, first let us write down the partition function for a single oscillator. It is given by 1 by 2 sine hyperbolic h bar omega into 2 kBt. So this is for a single oscillator. Now for an oscillator, we have to take the power n here. So this gives the partition function for n oscillators. So here we can write so 2 sine hyperbolic h bar omega 2 kBt to the power minus n. Now to find the free energy, that is the Helmholtz free energy, So f is given by minus kbt log of the partition function. So if I substitute here, then I will get n kbt log of 2 sine hyperbolic h bar omega 2 kbt. Now we have to find the free energy per oscillator in the low temperature limit. So better to work in the exponential term. So we can convert the sine hyperbolic to exponential term. So f is equal to kbt, and so log of, so we can write 2 into e to the power h bar omega 2 kbt minus e to the power minus h bar omega 2 kbt, and here we'll have a 2 factor here, so this 2 cancel out. Now t tends to 0, so when t tends to 0, so this term, so when t tends to 0, h bar omega 2 kbt will tends to infinite. So since this is e to the power minus, so this term will go to 0. Then we have n kbt log of e to the power h bar omega 2 kbt. So log and this exponential, then we can get f is equal to n kbt into h bar omega 2 kbt. So the Boltzmann constant cancels out. Then we can express f by n, that is free energy per oscillator. This is equal to h bar omega by 2. So option A is the correct answer. In this question, we are given a quantum harmonic oscillator in 2 dimensions with frequency omega. So since the omega is same in both the dimension, it is an isotropic quantum harmonic oscillator, and we have to find the partition function. Now let us write the energy. And from quantum mechanics, we know for 2D isotropic harmonic oscillator, we have 2 quantum numbers, nx and y, plus 1 by 2 plus 1 by 2 h bar omega. And since it is isotropic, here we can use a single quantum number n, which is equal to, here n is nx plus ny. Again, in isotropic 2D quantum oscillator, there is a degeneracy given by n plus 1. So using these 2 information, we can find the partition function. So partition function is given by summation, the degeneracy n plus 1 into e to the power minus n plus 1 h bar omega beta. Now if we expand this series, then we will get e to the power minus h bar omega beta plus 2 into e to the power minus 2 h bar omega beta plus 3 e to the power minus 3 h bar omega beta, and the series will go on. Now if I denote x is equal to e to the power minus h bar omega into beta, then this series looks something like this: x plus 2x squared 3x cubed plus 4x to the power 4, and this will go on. Now there are many ways to solve this series, and you can refer any standard textbook to solve this. So the sum of this series will be given by x divided by 1 minus x whole square. So if we substitute x, we have e to the power minus h bar omega divided by 1 minus e to the power minus h bar omega whole square. So option B is the correct answer. Now we will solve numericals on classical harmonic oscillator. So we are given n classical non-interacting particles subjected to a potential given by this, and we have to find the internal energy. So to solve this question, first we will find the average. First we'll write the Hamiltonian. So while writing the Hamiltonian, first I will do for 1 dimension, then later on we can go for 3 dimension, then for n particles in 3 dimension. So the Hamiltonian we can write p square by 2m plus v of x. So I'm writing for 1 dimension here. So the Hamiltonian here, p is nothing but px. So p square by 2m half of a r square. Sorry, ax square. Now let me write the partition function for this. So it will be a double integral exponential of minus beta p square by 2m plus half ax square dx dp. Now here one factor, 1 by h factor will be there, corresponding to the minimum size of the phase space, or we can say the phase cell. So here we have 1 by h. So if I take the integration of p here, then it will be beta p square by 2m dp, and integration of x, so e to the power minus half beta ax square dx. Now we can use the Gaussian integral here, that is integration of minus infinity to plus infinity e to the power minus a x square dx. This is given by square root of pi by a. So using this integration, we can write 1 by h. So this will be root over pi divided by beta by 2m, and the other integral will be root over pi divided by beta 2a. So we can simplify this and we will get 2 pi beta root over m by, let me just write it properly. So it will be m by k. Now in classical oscillator, root over m by k can be written as omega is equal to root over k by m. So one more h factor should be here. Yes. So this expression you can simplify as k beta t by h bar omega. So this is a very important formula, because without doing this integration, you can directly, if you know this formula, you can directly write as the partition function for a 1D classical harmonic oscillator is given by kbt by h bar omega. So this is for 1 dimension. So if I want to go for n particles in 3 dimension, then the partition function will be given by z1 to the power 3n. 3 for the 3 dimension and n for the n particles. So now we have our final partition function. It will be k beta t h bar omega to the power 3n. Now you can find the internal energy. So internal energy is given by kbt square del of log of z. So you can do the differentiation and you can get the final answer is 3n kbt. So I think it is matching with option A. In this question, we are given a two-dimensional harmonic potential and we have to find the canonical partition function. So first we will write the Hamiltonian of this system. So Hamiltonian is px square plus 2m plus py square 2m plus the potential, so alpha x square plus y square. So we can find the partition function for a single particle first. So single particle Z1 is equal to integration of exponential e to the power minus px square beta by 2m dpx. The integration will be from minus infinity to plus infinity. So then we can have we can write for the y component. So minus infinity plus infinity e to the power minus py square beta by 2m dpy. Then the x part, so it will be minus infinity to plus infinity e to the power minus alpha x square beta dx. Then integration minus infinity to plus infinity e to the power minus alpha y square beta dy. Now generally we put a factor here h. So here is, since it is 2 dimension, it will be h square. So to evaluate this 4 integral, we can use this integration formula, minus infinity to plus infinity e to the power minus ax square dx is equal to root over pi by a. So using this formula we can find, so this one will be root over pi by beta by 2m. Then the second integral will be pi divided by beta by 2m. The third integral we will have pi by alpha beta, and the fourth integral will have pi alpha beta. So we can simplify this and you'll get an expression 2 pi square m h square alpha by 1 by beta square. So this is the partition function for a single particle. So the partition function for n will be z1 to the power n, which is equal to 2 pi square m divided by h squared alpha beta square to the power n. So this is the partition function. But in the option, they have not considered 1 by h square factor. So if we exclude that, I think option D is the correct answer. Here we are given a classical nonlinear oscillator. Nonlinear because of this x to the power 4. Because when we differentiate this, we will get a force of x cubed. So we have to find the specific heat for an independent such oscillator. So what we will do first, we will find the partition. Oh, we have to find the specific heat. So we need to find energy. So what we will do, we'll write a Hamiltonian. Hamiltonian is already given here. So p square by lambda x to the power 4 Then we can find the average energy. So this will be equal to the average of the kinetic energy term and average of the potential energy term. Now, the average of the kinetic energy term will be given by, we have already discussed how to find the average value of kinetic energy term and potential energy term. So this will be equal to integration of p square 2m into the probability distribution, so p square beta by 2m dp divided by the partition function. So it will be e to the power minus p square beta 2m dp. Similarly, for the potential term, that is lambda x to the power 4, so this will be equal to lambda x to the power 4 e to the power minus lambda x to the power 4 beta dx divided by e to the power minus lambda x to the power 4 beta dx. Now we have to evaluate this integration. So to evaluate this integration, we can use this formula, 0 to infinity x to the power n, because here you can see the exponential term, it is x to the power 4, but in the previous question we have integrated for x square, so we need a more general formula. So this is the general formula, x to the power n e to the power minus ax to the power b dx. So this integration is given by 1 by b a to the power minus n plus 1 by b into gamma function of n plus 1 by b. So using this integration, we can find the average energy, right? We can find average energy. Then from this average energy, we can find the specific heat by using this relation. So the calculation is a bit lengthy, but using this trick you can solve it. Here we are given a particle confined in the region x greater than or equal to 0, and it is in a linear potential, and we have to find the mean position of the particle. Now for this, first we have to write the Hamiltonian. So Hamiltonian will be p square by 2m plus u naught into x. Then we can write the partition function. So partition function will be integration of e to the power minus Hamiltonian beta. So it will be double integral for one for p and one for x. So we have to find a mean position. So mean position will be equal to double integral of x e to the power minus Hamiltonian into beta dp dx divided by the partition function. Now we have to evaluate this integral, and this expression I can write like this. Average position is equal to integration of e to the power minus p square beta by 2m dp into integration of x e to the power minus u naught x beta dx divided by integration of e to the power minus p square beta by 2m dp into integration of e to the power minus u naught x beta into dx. So this one we can cancel out. So we already know the formula how to evaluate such type of integrals. So I'm writing the answer here. This one will be u naught beta square into gamma of 2 divided by 1 by u naught beta into gamma function of 1. So this cancels out and we have U naught beta, and this is kBt by U naught. So this is the answer. So it matches with option A. In this question, we are given a chain of 1D, one-dimensional chain consisting of n rods of each of length A, and each of these rods can align either parallel or perpendicular, and the energy of perpendicularly aligned rod will be minus epsilon. And what is the average length? So here I will write down, when it is perpendicular, the energy is minus epsilon. So in parallel, it will be plus epsilon. And let's say N1 are the number of rods which are aligned parallel, and N2 are the number of rods which are aligned in perpendicular. So this is like a two energy level problem. So the partition function of this will be e to the power minus beta epsilon plus e to the power plus beta epsilon. So this is the partition function. So the probability of staying in minus epsilon will be e to the power epsilon beta divided by e to the power minus epsilon beta plus e to the power plus epsilon beta. What about the probability for having plus epsilon? It will be e to the power minus epsilon beta divided by the partition function. So now we have got the probability of both this configuration. So what we can do, the rod of the length of each rod is A. So the average length we can write as A into N1, that is a number of rods in parallel configuration, into P of epsilon plus A and 2 P of minus epsilon. So with this we can calculate. So let us substitute. So it will be A N1 times e to the power minus epsilon beta. So the partition function factor will be common in both these terms. So I'm just writing A N2 here, e to the power epsilon beta divided by e to the power minus epsilon beta plus e to the power epsilon beta. So I can take this A common outside. Now here we can do one trick here, that is, if we consider these two probability, the denominator factors are the same, but in the numerator factor, one is exponentially decreasing and one is exponentially increasing. So this term will dominate over this term. So we can say that most of the rods will be in this configuration. So using that approximation, what I can do is, so N2 will be approximately equal to capital N. So An times e to the power epsilon beta divided by e minus epsilon beta plus e to the power epsilon beta. So I can divide the exponential term in the I can bring this down, the exponential term in the numerator to denominator. Then we will get n times a e to the power minus 2 epsilon beta plus 1. So this is the answer. So I think it is matching with option C. In this question, we are given a 3 energy level system, and it is told that the level with energy 0 has a degeneracy of 2, while the other are non-degenerate, and we have to find the average energy. So let me just draw the energy levels here. One is minus epsilon, 0 and plus epsilon, and this has degeneracy of 2 and 1 and 1. Now we can write the partition function now. So partition function is summation gi e to the power minus epsilon I beta. So e to the power plus epsilon beta plus 2e to the power 0 plus e to the power minus epsilon beta. So the partition function is 2 plus e to the power epsilon beta plus e to the power minus epsilon beta. Now we have got the partition function. So they are asking about energy. So average energy we can directly write by differentiating the log of partition function with respect to beta. So here you can beta, so it will be log of 2 plus e to the power epsilon beta plus e to the power minus epsilon beta. So this differentiation you can do it, and when you differentiate you will get a term like this. You can pause the video and you can do the differentiation. So I'm writing the final expression. It will be minus epsilon e to the power beta epsilon minus e to the power minus beta epsilon divided by, so 2 plus e to the power epsilon beta plus e to the power minus epsilon beta. So this is the term we get after differentiating. Now this term, the term in the partition, this term you can write as e to the power beta epsilon by 2 plus e to the power minus beta epsilon by 2 whole square, right? And this term we can use the formula a plus b into a minus b. Using this trick we can simplify it. So if you substitute, one of the terms will get cancelled out and you'll get this expression, e to the power beta epsilon by 2 minus e to the power minus beta epsilon by 2 divided by e to the power beta epsilon by 2 plus e to the power minus beta epsilon by 2, which is nothing but minus epsilon. So the exponential terms in the numerator, it's a sine hyperbolic function, and the term in the denominator is a cos hyperbolic function. So this will be 10 hyperbolic of beta epsilon by 2. So this is the answer. So I think it is matching with option D.